The night sky has always been a canvas of wonder, but every so often, it presents a puzzle so profound that it shakes the very foundation of what we thought we understood. In the early years of the 21st century, astronomers encountered such a riddle in the form of a star catalogued as JWST. When its discovery was announced in the year 2002, it seemed at first like another faint point of light in the remote halo of the Milky Way. Yet within its faint spectrum lay a secret that would force scientists to rethink the story of how stars are born and how the universe itself evolved. To understand why this object startled the scientific community, one must appreciate the language that astronomers use to describe stars. At its core, every star is made primarily of hydrogen and helium, the simplest and lightest elements forged in the aftermath of the Big Bang. Everything heavier, whether carbon, oxygen, iron, or gold, was created later in the furnaces of stars and spread across space when those stars exploded. Astronomers call these heavier elements metals, even though, in everyday life, we would not consider oxygen or carbon to be metals. This peculiar shorthand leads to the concept of metallicity, which measures the fraction of a star's mass composed of anything heavier than helium. For decades, models of the early universe predicted that the very first stars, often called population 3 stars, were massive, short-lived, and composed entirely of hydrogen and helium. These giants were thought to have perished within a few million years, leaving behind no survivors for us to see today. Later generations of stars, enriched with the elements dispersed by those early explosions, should contain at least a detectable amount of metals. Thus, by the dawn of the 21st century, the consensus was that no long-lived, metal-free star could still be shining. And yet, He0107524 seemed to mock this belief. Its spectrum revealed an iron content so minuscule that it amounted to roughly 1/200,000th of the iron present in our Sunday. To put this into perspective, if you could melt the entire sun into a gigantic cosmic cauldron and scoop out a single spoonful, the amount of iron in that spoon would be greater than all the iron inside this ancient star. The numbers were so extreme that many wondered if they were even real. The discovery did not stand alone for long. In the year 2011, another star joined the ranks of the impossible. This one, catalogued as SDSS J102915+172927, was found to be similarly primitive. What made it even more remarkable was its lack of enrichment in carbon and oxygen, elements that some theorists had argued were necessary for the cooling of gas clouds in the early universe. Without such cooling, low-mass stars should not have been able to form. Yet here it was, glowing faintly in the halo, daring astronomers to explain how it came to exist. To those steeped in the equations of stellar formation, these discoveries were like finding a handwritten note in an ancient ruin that seemed to be written in the future tense. They did not fit with the accepted timeline of cosmic evolution. If these stars were true survivors from the dawn of time, then our models of the first stars were missing something fundamental. If, on the other hand, they had acquired their strange chemical fingerprints through some other process, then we had misread the evidence. In both cases, the stakes were high, for the story of how matter assembled into stars is inseparable from the story of how galaxies formed and how the conditions for life eventually emerged. The shock reverberated across the field because metallicity is not just an abstract number. It is a bridge between theory and observation, a marker of how many generations of stars have lived and died before a given star was born. High metallicity implies a rich history of stellar recycling, while extremely low metallicity suggests proximity to the beginning of time itself. To find a star with metallicity so low was to stumble upon a fossil that seemed older than the laws that allowed its creation. In the years following these announcements, telescopes across the world turned their gaze to such enigmatic stars. High-resolution spectrographs, instruments capable of separating light into its constituent wavelengths with exquisite precision, became the tools of cosmic forensics. The faint fingerprints of atoms etched across a spectrum told astronomers not just what elements were present, but in what relative amounts. These chemical codes carried whispers from an era when the universe was only a few 100 million years old. For the general public, the headlines were tantalizing. Phrases like "star older than the universe" were splashed across newspapers, even though scientists were careful never to claim such impossibilities. What they did say was that these stars pushed against the edges of current models. If one accepts that our knowledge of physics is incomplete at such extremes, then these stars acted as beacons, pointing us toward the gaps in our understanding. Every mystery demands a closer look at the tools used to uncover it, and this case is no exception. The discoveries of JWST and SDSS J102915+172927 were not accidents. They were the fruits of systematic sky surveys and painstaking analysis, where vast catalogues of stars were sifted to find the rarest needles in a cosmic haystack. To fully grasp how such improbable stars were identified, we must step into the realm of stellar archaeology, where the night sky is read like an archive, and light itself becomes a record of ancient events. And so, from the spark of astonishment, comes a journey into method. How do astronomers measure the chemistry of stars so faint that they barely register on detectors? How do they assign ages to objects older than any human imagination can easily hold? The answers lie not in guesswork, but in techniques honed over a century of astrophysics, where the humble spectrum becomes a time machine and the positions of stars trace the motions of galaxies long consumed. It is here, in the quiet labor of measuring and comparing, that the story of impossible stars moves from discovery to explanation, and from wonder to the disciplined pursuit of truth. The universe is often described as a grand laboratory, but unlike earthly experiments, its processes cannot be repeated at will. We cannot rerun the Big Bang to see what would happen if the conditions were slightly different, nor can we watch a star live and die in real time across billions of years. Instead, we rely on the light that has traveled across space and time, carrying within it a record of physical conditions long past. This is the essence of stellar archaeology, the practice of reading the ancient sky to reconstruct the earliest chapters of cosmic history. At the heart of this practice is spectroscopy. When light from a star is passed through a prism or a diffraction grating, it spreads into a rainbow of colors. Within this rainbow, dark lines appear where specific wavelengths of light have been absorbed by atoms in the star's atmosphere. Each element produces a unique set of lines, much like a fingerprint. By measuring the depths and positions of these lines, astronomers can determine not only which elements are present, but also their relative abundances. It is this ability to read the fine details of spectra that allows us to claim that a star like JWST contains a vanishingly small amount of iron, or that SDSS J102915+172927 lacks the expected enrichment of carbon and oxygen. Spectroscopy is not just about detection, it is about precision. The faintest metal-poor stars challenge even the most sensitive instruments. To study them, astronomers employ large telescopes, such as the Very Large Telescope in Chile or the Keck Observatory in Hawaii, equipped with spectrographs capable of measuring the width of a hair at the distance of a kilometer. Observations often require hours of careful exposure, collecting enough photons to tease out patterns that would otherwise be lost in noise. The resulting spectra are then compared with theoretical models of stellar atmospheres, where assumptions about temperature, gravity, and turbulence are adjusted until the observed lines match the predicted ones. But chemistry alone cannot tell us the age of a star. To estimate when it was born, astronomers turn to another tool, the Hertzsprung-Russell diagram, which plots stars according to their brightness and temperature. By comparing a star's position on this diagram with theoretical evolutionary tracks, one can infer its approximate age. For populations of stars, isochrones are used, curves that connect stars of the same age but different masses. These tools, while powerful, are not perfect. They rely on assumptions about nuclear reaction rates, energy transport, and opacity, each of which introduces uncertainties. Beyond individual measurements, large-scale surveys have transformed our understanding of the stellar population. The Sloan Digital Sky Survey, launched at the turn of the 21st century, mapped millions of stars, galaxies, and quasars with unprecedented detail. Its vast catalogue provided the initial data that led to the discovery of stars like SDSS J102915+172927. Other surveys, such as SkyMapper in Australia, have specialized in searching for extremely metal-poor stars by selecting candidates with particular colors in their photometry, which are then followed up with spectroscopy. Perhaps the most transformative contribution has come from the Gaia mission, launched by the European Space Agency in 2013. Gaia has measured the positions, motions, and distances of more than 1 billion stars with extraordinary accuracy. For the study of ancient stars, this means not only knowing their chemical composition, but also tracing their orbits through the galaxy. Some stars move in loops that suggest they were born in the Milky Way, while others follow paths, indicating that they were accreted from dwarf galaxies long ago. These kinematic signatures add a layer of history, showing how the Milky Way grew by merging with smaller systems. Despite these advances, uncertainties remain stubborn companions. Stellar spectra can be affected by assumptions about three-dimensional convection in atmospheres, or by departures from perfect equilibrium in the populations of atoms. Tiny errors in measuring line strengths can lead to significant changes in inferred abundances when dealing with extremely metal-poor stars. Similarly, age estimates carry uncertainties of billions of years, which matters greatly when trying to distinguish between stars formed 200 million years after the Big Bang and those formed a billion years later. This blend of precision and uncertainty is what gives stellar archaeology its character. It is a science built on faint signals, where every photon is precious and every assumption must be tested. Yet it is also a science that delivers profound insights. By reading the chemical DNA of stars, we peer into a time before galaxies, as we know them, existed, when the universe was still clearing from the haze of its infancy. The methods of stellar archaeology do more than identify anomalies. They build a framework that allows us to confront theory with observation. If stars with impossibly low metallicity exist, then our models of the first stars must adapt. If such stars are never found despite increasingly sensitive searches, then our confidence in current theory grows. Either way, the outcome sharpens our understanding, and so the story moves forward. With the tools of spectroscopy, photometry, and astrometry, astronomers have mapped the chemical and dynamical landscapes of the Milky Way. They have sifted through billions of stars to uncover a handful of survivors whose very existence defies prediction. These discoveries bring us face to face with the theoretical population. 3 stars, the first generation born from pristine hydrogen and helium. Were they truly giants that burned out swiftly, leaving no survivors? Or could some low-mass members have endured to the present day, hidden among the faintest points of light in the halo? To answer this question, we must step into the world of theory, where cosmology and astrophysics converge. We must revisit the early universe itself, a time when no metals existed, when cooling of gas clouds was governed only by the simplest molecules, and when gravity alone determined whether stars could form. It is here, in the birthplaces of the first stars, that the riddle of impossible survivors begins. The first stars occupy a unique place in our cosmic imagination because they represent a beginning that no one could witness, yet every atom in our bodies ultimately depends on. To understand why the discovery of extremely metal-poor stars is so astonishing, we must return to the epoch when the universe was only a few minutes old. In that brief span, as the primordial fireball cooled, protons and neutrons fused to form the lightest nuclei. Hydrogen dominated, helium was created in significant amounts, and a trace of lithium appeared, but nothing heavier could be forged. The newborn cosmos was therefore almost featureless in its chemistry. When gravity began gathering matter into clumps, these pristine gas clouds faced a challenge. To collapse into stars, gas must lose energy. Cooling is the gatekeeper that allows gravity to succeed. In today's universe, cooling is aided by atoms and molecules of carbon, oxygen, and other metals, which radiate energy efficiently. But in the early universe, with no metals at hand, the only available coolant was molecular hydrogen. It could radiate energy away, but not nearly as effectively as heavier elements. For decades, simulations of star formation suggested that under such limited cooling, the first stars must have been enormous, with masses tens or even hundreds of times that of the Sun. Such stars, by their very nature, could not live long. A massive star burns through its nuclear fuel rapidly, its core running at temperatures so high that fusion reactions proceed with relentless speed. Within a few million years, these giants would exhaust their fuel, collapse, and explode as supernovae, scattering their newly forged heavy elements into space. The cycle of cosmic enrichment would then begin, enabling the next generation of stars to form with traces of metals. According to this framework, by the present day, there should be no survivors from that primordial generation. Any star we see now must have at least some metals in its makeup, for it would belong to later generations. Yet the existence of stars like JWST and SDSS J102915+172927 suggests another possibility. Could it be that under certain conditions, Small stars formed even in the absence of efficient cooling. Low-mass stars live for billions of years, longer than the current age of the universe. If any low-mass population 3 stars were born, they could still be shining today. Their discovery would be nothing less than a window into the universe's first stellar generation. The problem is that no truly metal-free star has ever been confirmed. Every candidate studied so far contains at least a trace of metals, sometimes enriched in carbon or other light elements. The question then becomes whether these stars are genuine survivors from the primordial era, or whether they belong to the very next generation, formed from gas that had been touched lightly by the ashes of the first supernovae. If they are survivors, they are fossils from the dawn of time. If not, they are still remarkable, for they preserve the chemical signature of the first explosions. The stakes in this debate are enormous. Knowing whether low-mass population 3 stars exist would tell us how efficient cooling really was in the young universe. It would constrain models of dark matter halos, where gas first collected, and it would refine our understanding of the transition from a dark cosmos to one filled with starlight. Without clarity on this issue, our picture of early cosmic evolution remains blurred. Observations, however, do not always align neatly with theory. The chemistry of the most metal-poor stars often shows unusual ratios of elements. Some display elevated carbon compared with iron, suggesting that they formed from the debris of a faint supernova, one that failed to mix its innermost products into space. Others show patterns that hint at accretion, where a star that formed metal-free later picked up material from the interstellar medium. Each possibility complicates the story, reminding us that nature rarely follows simple categories. Astronomers continue to push the limits of detection, scouring the halo and dwarf galaxies for stars with even lower metallicities. Each new candidate is scrutinized with the best instruments, its spectrum dissected for the faintest lines. The hope is that one day, perhaps soon, a star with no detectable metals at all will be found. Such a discovery would confirm that low-mass population 3 stars can exist and would provide a living relic from an epoch otherwise accessible only through simulations. As we contemplate these stars, it becomes clear that they are more than curiosities. They are signposts, pointing back to the formative stages of structure in the universe. Their existence or absence informs our models of how galaxies assembled, how the first black holes grew, and how the chemical ingredients of life spread across space. In their faint light is encoded the transition from a cosmos of simplicity to a cosmos of complexity. Thus, the puzzle of the star that should not exist is not an isolated problem. It is a challenge to our narrative of cosmic history. Each faint spectrum, each anomalous ratio of elements, each contradiction between observation and theory forces us to revisit the assumptions on which our understanding is built. Science thrives on such tensions, for they are the seeds of progress. The chapter of impossible stars does not close with their discovery. Rather, it opens the door to the broader, theoretical landscape of how stars formed in the first place. To continue this journey, we must shift our gaze from the individual spectra to the simulations and calculations that attempt to model the early universe. Only by examining how the first generation of stars should have arisen and why we thought they could not survive, can we truly appreciate the significance of the improbable survivors that gleam today in the halo of our galaxy. The search for the oldest stars is not a romantic wandering of telescopes across the heavens. It is a deliberate and methodical science that treats the night sky as an archive, one that must be read with care and precision. Each star holds a record of its birth, inscribed not on stone tablets or fragile scrolls, but within the light it emits. To unlock this record, astronomers employ the techniques of stellar archaeology, a discipline that seeks to piece together the history of the cosmos by reading the chemical codes of ancient stars. At first glance, the light of a star seems uniform. Our eyes register only a color, a faint twinkle against the darkness. But when that light is passed through a spectrograph, it reveals its hidden structure. The rainbow of colors spreads out like a map, interrupted by thin, dark lines. These are absorption lines, signatures of atoms and ions in the star's outer layers. Each element absorbs light at specific wavelengths, leaving behind a fingerprint. By carefully measuring the depths and shapes of these lines, astronomers can determine the abundance of elements in a star with remarkable precision. This process is akin to extracting a strand of DNA and decoding the instructions written in its sequence. The practice of spectroscopy is not new. It was in the 19th century that scientists like Joseph Fraunhofer and Gustav Kirchhoff first noticed and explained the absorption lines in sunlight. They realized that each line corresponded to a transition between energy levels in atoms, a connection between physics on Earth and the behavior of matter in distant stars. That insight opened the path to a new kind of astronomy, one not limited to brightness and position, but able to reach into the very chemistry of the universe. By the time the 20th century drew to a close, spectroscopy had become the backbone of stellar research. For stellar archaeologists, the challenge lies in pushing this technique to its limits. The stars of greatest interest are not the bright beacons of the disk, but the faint, ancient stars that linger in the galactic halo. These stars are dim precisely because they are old and low in mass. To study them requires the largest telescopes available. Instruments like the high-resolution Echelle spectrograph at the Keck Observatory or the ultraviolet and visual Echelle spectrograph at the Very Large Telescope are capable of capturing the delicate structure of spectra from objects that are barely detectable. The task demands patience. Hours of exposure gather enough photons to distinguish the faint absorption lines from noise. Each line must then be modeled, accounting for temperature, gravity, and even the turbulent motions of gases within the star's atmosphere. The data that result are both powerful and fragile. A misjudgment about the star's surface temperature or a simplification in the model can shift abundance estimates significantly. Stellar archaeology is a science of careful error bars, where every claim of a low metallicity must be supported by rigorous analysis. Yet when done well, the method yields extraordinary revelations. It can tell us that one star contains less than 1 part in 100,000 of iron compared with the Sun, or that another bears the signature of carbon enhancement likely produced by a faint supernova. Beyond individual stars, surveys have transformed the field. The Sloan Digital Sky Survey, launched at the turn of the century, collected spectra for millions of celestial objects, mapping vast regions of the sky. Within its treasure trove, astronomers discovered candidates for extremely metal-poor stars by identifying those with unusually weak absorption lines of iron. SkyMapper, an Australian project, refined the search by using photometric filters designed to highlight metal-poor candidates before following them up with spectroscopy. These surveys turned the hunt for ancient stars from a matter of chance into a systematic enterprise. Even more revolutionary has been the Gaia mission. By measuring the positions, motions, and distances of over 1 billion stars with exquisite accuracy, Gaia has provided a dynamic view of the Milky Way. For stellar archaeologists, this means that chemistry can be combined with motion. A star's orbit reveals whether it was born in the Milky Way, or whether it was captured from a smaller galaxy that merged with ours. The chemical signature and the orbital path together form a narrative: where the star came from, what environment it formed in, and how it became part of our galactic family. The discipline also confronts its limitations honestly. No measurement is free from uncertainty. Line strengths can be influenced by assumptions about equilibrium, and small shifts in calibration can alter results. Models of stellar atmospheres often simplify complex processes like convection or magnetic activity. For the faintest stars, even obtaining enough photons to study is a monumental task. The limits of technology define the edges of knowledge, and stellar archaeologists are always pressing against those edges. Yet even with these uncertainties, the field continues to make progress. Each new discovery of an ultra-metal-poor star adds a piece to the puzzle of the early universe. Each refinement in the models sharpens our picture of stellar formation. The process is cumulative, building layer by layer, much as archaeologists on Earth reconstruct history from fragments of pottery and stone. The wonder of stellar archaeology lies in its ability to take something as intangible as light and turn it into a chronicle of cosmic history. Every photon captured by a spectrograph has traveled across space and time, carrying with it the signature of ancient nuclear processes. To read those photons is to reach across billions of years and touch the infancy of the universe. From this foundation of method and measurement arises the next stage of the story, where theory takes the lead. The observations of faint ancient stars point us toward the possibility of an earlier generation, the population 3 stars. To understand why their absence or presence matters, we must turn from the tools of observation to the predictions of cosmology and consider what the universe should have produced in its earliest moments of star formation. The work of stellar archaeology is as much about patience as it is about ingenuity. When astronomers peer through their telescopes at the faintest points of light in the galactic halo, they are not looking for beauty alone. They are searching for the rarest chemical signatures, traces of a time when the cosmos was still young. This search requires a careful layering of methods, each reinforcing the other, until a coherent picture begins to emerge from the noise. One of the most remarkable aspects of this discipline is its reliance on spectroscopy as the universal translator of starlight. Each line etched into a spectrum represents an electron within an atom, shifting from one energy level to another. These transitions are dictated by the laws of quantum mechanics, which means they are the same everywhere in the universe. A hydrogen atom in a distant star behaves exactly as a hydrogen atom in a laboratory on Earth. This universality is what allows astronomers to decode light from stars thousands of light years away and trust that the information it carries is reliable. Yet, the interpretation of that light is not simple. A spectrum is not a pristine record, but a layered one. It must be corrected for instrumental effects, atmospheric interference, and the motion of the Earth itself. The background glow of the night sky can obscure faint lines, and even the tiniest imperfections in a spectrograph can leave their mark. Every dataset must be calibrated, cross-checked, and compared against standards. The process can take months for a single star, but the reward is a glimpse into a chemical composition that has remained unchanged for billions of years. Age estimation presents its own set of challenges. Stars do not come with birth certificates, and astronomers must infer their ages indirectly. One method involves comparing a star's properties with theoretical models of stellar evolution. As a star ages, it moves across the Hertzsprung-Russell diagram, shifting in brightness and temperature. By finding the theoretical curve, or isochrone, that best matches the observed data, astronomers can estimate the star's age. This is a delicate task, as small uncertainties in temperature or brightness can lead to differences of billions of years in the inferred age. Another avenue is kinematics, the study of motion. Thanks to Gaia, we now know the precise orbits of many halo stars. If a star moves in a path typical of ancient populations, plunging through the galaxy in elongated orbits far from the disk, it is likely to be old. These orbital signatures, combined with chemistry, create a fuller picture. A star with extremely low metallicity and an ancient orbit is a prime candidate for having formed in the early universe. Despite the care taken, uncertainties remain. Models of stellar atmospheres often assume equilibrium, where the populations of atoms in different energy states balance perfectly. In reality, non-equilibrium effects can alter line strengths. Similarly, convection in stellar surfaces introduces three-dimensional structures that cannot be captured by simple models. These complications mean that abundance estimates always carry margins of error, yet even with these uncertainties, the relative comparisons remain valid. When a star shows abundances thousands of times lower than the Sun, no amount of modeling error can erase the conclusion that it is truly primitive. Large-scale surveys amplify this effort by providing context. A single star might be an anomaly, but when hundreds of stars are catalogued with varying metallicities, patterns emerge. The distribution of metallicity across the halo reveals the chemical history of the galaxy, showing how successive generations of stars enriched their environments. Extremely metal-poor stars sit at the tail of this distribution, rare outliers that point back to the earliest times. Their scarcity makes them precious, like fossils of creatures that lived in the first dawn of life on Earth. One particularly striking insight from these surveys is the discovery that some metal-poor stars are not randomly scattered, but are concentrated in certain regions or move in groups. This suggests that they may have been born in dwarf galaxies that were later swallowed by the Milky Way. In this way, stellar archaeology not only uncovers the chemistry of stars, but also reconstructs the galactic mergers that built the Milky Way itself. Every improvement in technology deepens the reach of this science. The advent of adaptive optics, which corrects for the blurring effect of Earth's atmosphere, allows telescopes to resolve fainter stars with greater clarity. High-efficiency detectors capture more photons, reducing the time required for long exposures. Future observatories, such as the Extremely Large Telescope and the Vera Rubin Observatory, promise to extend the search to even dimmer and more distant stars. These tools may well uncover stars whose metallicities are lower than any yet observed, perhaps even revealing the elusive first-generation survivors. The practice of stellar archaeology underscores a fundamental truth about science. Progress is incremental, but the implications can be vast. By reading the light of a single faint star, astronomers can infer events that occurred billions of years ago, when the first galaxies were assembling. Each measurement adds to a growing tapestry of knowledge, one that binds observation to theory and grounds speculation in evidence. And so the story moves forward, from the painstaking work of measuring spectra and orbits, to the broader question of what these observations mean. If the universe began with only hydrogen, helium, and traces of lithium, and if theory tells us that the first stars should have been massive and short-lived, then why do we find faint, long-lived stars with metallicities so low? The answer lies not in observation alone, but in the marriage of data with cosmological models. To pursue it, we must now follow the thread into the realm of theory, where the population 3 stars await, hovering at the edge of existence between prediction and discovery. The search for the oldest stars is a pursuit of origins, and every tool of stellar archaeology sharpens the question of what the first generation of stars might have looked like. Yet as the techniques become more refined, the riddle deepens rather than dissolves. The stars we find in the galactic halo, in dwarf galaxies, and in the outskirts of the Milky Way tell a story of extreme scarcity in metals, but none have been found to be entirely free of them. This subtle but crucial detail keeps astronomers poised between confidence and uncertainty. To appreciate the depth of the mystery, imagine tracing human ancestry back through generations. Each parent leaves genetic signatures that accumulate in the child. By comparing DNA across many individuals, we can reconstruct lineages stretching far into the past. Stellar archaeology functions in much the same way. Every supernova injects heavy elements into the interstellar medium, enriching it for the next cycle of star formation. If we observe a star with a certain metallicity, we are essentially reading the number of ancestral explosions that contributed to the gas cloud from which it formed. The lowest metallicity stars are like descendants with the fewest ancestors, and their DNA points us back toward the very first families of stars. Surveys have revealed that these extremely metal-poor stars are exceedingly rare. For every 100,000 stars in the Milky Way, only a handful exhibit metallicities less than 1/10,000th of the Sun's. To find them is like searching for a single grain of sand in a desert, and yet these rare grains hold the power to reshape our understanding of cosmic history. Their abundance patterns, the ratios of carbon to oxygen or magnesium to iron, cannot be explained by ordinary stellar processes alone. They suggest the fingerprints of unusual supernovae, explosions that ejected some elements while retaining others deep within their collapsed cores. This realization has led astronomers to propose the existence of faint supernovae. Unlike the spectacular explosions that seed space with heavy elements in a uniform manner, faint supernovae may have dispersed only the lighter products of nuclear fusion, while keeping iron locked within their remnants. A star forming from such material would then display extremely low iron, but elevated levels of carbon or magnesium. Observations of certain metal-poor stars match these predictions, reinforcing the idea that the earliest enrichment events were not uniform, but diverse and complex. The role of dwarf galaxies adds another layer of intrigue. These small, faint systems are believed to be the building blocks of larger galaxies. Many of them still orbit the Milky Way today, and their stellar populations are dominated by ancient stars. Spectroscopic surveys of dwarf galaxies have uncovered stars with metallicities nearly as low as those found in the halo, suggesting that some of the oldest chemical records are preserved outside the main body of the Milky Way. These discoveries support the notion that our galaxy grew by accreting smaller systems, each bringing its own population of stellar fossils. Gaia's mapping of stellar motions has confirmed this picture. Some of the halo stars with the lowest metallicities follow orbits that trace back to ancient mergers. They are not native to the Milky Way, but immigrants, carrying with them the chemical imprints of environments long since disrupted. Stellar archaeology thus becomes not only a study of chemistry, but also a history of migration, revealing the pathways by which the Milky Way assembled itself. With every advance, however, the uncertainties persist. Stellar ages remain difficult to pin down, with margins of error stretching across billions of years. Spectroscopic models struggle to capture the full complexity of stellar atmospheres. Surveys may be biased towards stars that are easier to detect, leaving the faintest and most ancient still hidden. The field is a constant dialogue between optimism and caution, between discovery and humility. What has become clear is that the story of star formation is richer than once believed. The universe did not transition cleanly from metal-free giants to metal-rich dwarfs. Instead, there appears to have been a turbulent period of diversity, with faint supernovae, dwarf galaxies, and varied environments producing stars of wildly different chemical compositions. The halo stars we see today are the survivors of that chaotic era, frozen records of conditions that no longer exist. The discipline of stellar archaeology thrives on these tensions. It is not a field where mysteries are quickly solved, but one where each answer opens new questions. By refining techniques, building larger surveys, and designing ever more sensitive instruments, astronomers edge closer to the truth. Yet the truth itself may be more complex than the simple models of early star formation once suggested. The search continues, relentless and patient, driven by the conviction that somewhere in the darkness, a star still shines that has never known the touch of heavy elements. Finding such a star would confirm the survival of population 3, rewriting our understanding of the first chapter of stellar evolution. Even if such a star remains elusive, the attempt illuminates the pathways by which the cosmos transformed from simplicity to complexity. And so the methods of stellar archaeology, painstaking and precise, bring us to the threshold of theory. With spectra and surveys in hand, we now turn to the predictions of cosmology. What exactly should the first stars have looked like? How massive were they? How bright? And how short-lived? To answer these questions, we must leave the realm of observation and step into the models of population 3, the primordial giants, whose existence remains both certain and mysterious. In the silence that followed the Big Bang, the universe was a sea of simplicity. For hundreds of thousands of years, it was filled only with expanding gas composed of hydrogen, helium, and a trace of lithium. The light of the cosmic microwave background faded into a chill darkness, and gravity began to stir the otherwise uniform expanse. Slowly, matter gathered into denser regions, forming the first halos of dark matter and gas. Out of these halos would come the very first stars, a generation unlike any that followed. Astronomers call them population 3 stars, a label that belies their extraordinary importance. To understand these primordial stars, we must remember that everything heavier than helium did not yet exist. The oxygen we breathe, the carbon that forms the backbone of life, the iron in our blood, none of these were present. The early universe was chemically barren, and this fact shaped how the first stars were born. For gas clouds to collapse into stars, they must cool and shed energy. In the modern cosmos, cooling is aided by atoms and molecules of heavier elements that radiate heat efficiently. But in a pristine universe with only hydrogen and helium, the only significant coolant was molecular hydrogen, a fragile molecule that forms in small amounts. Simulations of this era reveal a striking picture. In the absence of strong cooling, gas clouds did not fragment into many small stars, but collapsed into a few massive ones. These stars are predicted to have been enormous, some with masses tens or even hundreds of times that of the Sunday. Their immense weight drove their cores to extreme pressures and temperatures, igniting nuclear fusion at a furious pace. Unlike the Sun, which will live for about 10 billion years, such giants would burn through their fuel in only a few million years, an eye blink in cosmic time. The short lives of population 3 stars mean that none of them should survive today. Their deaths, however, were cataclysmic. Many are thought to have ended as supernovae, scattering newly forged heavy elements into the surrounding space. Others may have collapsed directly into black holes, seeding the cosmos with the first dark behemoths that would later grow into the supermassive black holes we observe at the centers of galaxies. In either case, the role of population 3 stars was transformative. They ended the cosmic dark ages by flooding the universe with light, they enriched the gas with metals, and they set the stage for all subsequent generations of stars. The evidence for their existence is indirect, but compelling. The abundance patterns observed in the most metal-poor stars today hint at enrichment by very unusual explosions. Some show enhanced carbon and magnesium, but very little iron, suggesting that the progenitor supernovae ejected their outer layers but retained much of their cores. These fingerprints align with predictions for the first stellar deaths. Similarly, observations of distant galaxies with the James Webb Space Telescope have revealed signs of extremely hot and massive stars, candidates for population 3, though confirmation remains uncertain. Population 3 stars also play a key role in theories of reionization, the epoch when ultraviolet light from the first luminous sources stripped electrons from hydrogen atoms, making the universe transparent once more. Their intense radiation, combined with the birth of the first galaxies, transformed the cosmos from a foggy darkness into the structured universe we see today. Without them, the timeline of cosmic evolution would be unrecognizable. Yet, the paradox remains. If all population 3 stars were massive and short-lived, why do we observe ancient stars in the halo of the Milky Way that seem almost devoid of metals? Are these second-generation stars, formed from gas only lightly enriched by the first supernovae, or are they the impossible survivors of population 3 itself? The distinction is profound. A confirmed low-mass population 3 star would provide a living laboratory for conditions that otherwise exist only in theory. Its chemistry would be pristine, untainted by any supernova, a direct echo from the dawn of time. The search for such survivors continues, guided by both observation and simulation. Computational astrophysics has advanced to the point where detailed 3-dimensional models of star formation in the early universe can be run. These simulations explore how gas cooled, how it fragmented, and under what conditions small stars might form, even without metals. The results suggest that while most population 3 stars were indeed massive, there may have been rare pathways to lower mass stars. If so, the possibility remains that a few such objects are still shining faintly in the Milky Way today, awaiting discovery. As we consider these predictions, we are reminded of the role theory plays in shaping observation. Without the models, astronomers would not know what to look for or what signatures to expect. Without observation, the models would remain untested abstractions. The dialogue between the two is where progress is made. The faint spectra of halo stars, the chemical codes inscribed within them, and the simulations of primordial gas clouds all converge on the same mystery. What truly were the first stars, and how did they shape the universe that followed? The stage is set, then, for a confrontation between prediction and evidence. Population 3 stars are central to our story, both as a theoretical necessity and as a haunting absence. They should have existed, they must have died, but whether any linger is unknown. To pursue this question further, we must now return to the observational record, where the most extreme metal-poor stars ever discovered challenge every expectation, daring us to reconcile their existence with the tale of population 3. The birth of the first stars is a subject that demands imagination as much as calculation. In the pristine void of the early cosmos, the laws of physics operated with an austere simplicity. There were no heavy elements to complicate cooling, no dust grains to seed new structures, no prior generations of stars to enrich the medium. Under these conditions, gas clouds collapsed slowly and reluctantly, guided only by the faint cooling of molecular hydrogen. The result, according to decades of simulations, was the creation of stars unlike any that shine today. Population 3 stars are predicted to have been titans. Their immense masses meant their surfaces blazed at temperatures far hotter than the Sunday. They poured out ultraviolet radiation in torrents, bathing their surroundings with energetic photons capable of stripping electrons from hydrogen atoms. This radiation was powerful enough to begin carving bubbles of ionized gas around them, small pockets of clarity within a foggy universe. When multiplied across many such stars and early galaxies, these bubbles overlapped, and the universe underwent reionization, a pivotal transformation that lifted the cosmic veil and allowed light to travel freely once more. The deaths of these stars were equally momentous. The heaviest among them may have died as pair instability supernovae, explosions so violent that the star was entirely disrupted, leaving no remnant behind. Such events would have spread enormous amounts of heavy elements into space, enriching their surroundings far more dramatically than ordinary supernovae. Slightly smaller population 3 stars may have collapsed into black holes, swallowing their cores and seeding the growth of the first massive black holes. These remnants are of special interest, for they may explain how supermassive black holes already existed less than 1 billion years after the Big Bang, a mystery that still challenges astrophysics today. The chemical imprints of these primordial events linger in the stars that formed afterward. When astronomers examine the elemental ratios in ultra-metal-poor stars, they sometimes find patterns that match the predictions of faint or pair instability supernovae. For example, a star with a high ratio of carbon to iron suggests enrichment by an explosion that expelled carbon-rich outer layers but retained iron deep inside. These patterns act as fossil records, telling us about supernovae that occurred more than 13 billion years ago. Despite this indirect evidence, the absence of direct detection gnaws at the edges of certainty. Population 3 stars remain hypothetical, seen only through their consequences. Observations with the James Webb Space Telescope have pushed the frontier back to galaxies less than 400 million years after the Big Bang. Some of these galaxies emit light so blue and so intense that they may contain population 3 stars, but the signals are faint and the interpretations debated. Confirmation will require more time, more data, and perhaps new instruments yet to be built. Another line of inquiry lies in the realm of gravitational waves. The mergers of massive black holes, detected by instruments like LIGO and Virgo, may provide clues to the remnants of population 3 stars. If the earliest black holes merged in great numbers, their echoes could still reverberate today, detectable as a background of gravitational waves. Such signals, though challenging to isolate, could offer an entirely new way of probing the lives and deaths of the first stars. The central paradox remains stark. If all population 3 stars were truly massive, none should survive. Yet, the discovery of extremely metal-poor stars with properties that strain explanation leaves the door open. Could some rare conditions have allowed small population 3 stars to form? Perhaps cooling by molecular hydrogen, while inefficient, occasionally produced fragments small enough to yield long-lived stars. Or perhaps the gas clouds were influenced by dark matter in ways not yet understood, enabling a diversity of outcomes. Simulations are divided. Some predict a strict absence of low-mass population 3 stars, others suggest a small but finite possibility. The debate is lively, with each new observation fueling arguments on both sides. What is certain is that the survival of even a single such star would be revolutionary. It would provide direct access to the pristine conditions of the early universe, allowing astronomers to test theories of primordial nucleosynthesis, cooling, and star formation with unmatched precision. In this light, the faint halo stars that confound astronomers today take on even greater significance. They may not be pristine, population 3 survivors, but they are the closest we have. Their spectra carry the echoes of the first supernovae, and their very existence challenges the neat categories of theory. They are the messengers of an era just beyond reach, telling us that the early universe was more complex, more varied, and more unpredictable than the simple models once suggested. The story of population 3 stars is not one of closure, but of pursuit. They stand at the boundary between the known and the unknown, necessary to explain the universe we see but elusive in their details. To reconcile their predicted grandeur with the humble faint stars we actually observe, we must confront contradictions head-on. It is in this confrontation that the narrative of the impossible survivors gains its sharpest edge, pressing us to reconsider what we thought we knew about the dawn of starlight. The paradox of population 3 stars continues to haunt modern astrophysics because it sits at the boundary between inevitability and impossibility. On the one hand, theory insists that they must have existed. Without them, the universe would never have transitioned from a chemically barren expanse to one rich in the elements needed for planets and life. On the other hand, their absence in the present sky is equally inevitable if they were all massive and short-lived. The tension between these two truths creates a scientific drama that unfolds in every faint spectrum of every ancient star we study today. The quest for answers begins with simulations. Over the past 2 decades, computational astrophysics has made it possible to follow the collapse of gas clouds in the early universe, from initial density fluctuations to the ignition of nuclear fusion. These simulations suggest that the lack of heavy elements prevented efficient cooling, leading to clumps of gas that grew enormous before collapsing. Out of these clumps emerged stars so massive that they burned at blistering temperatures and lived only a few million years. The calculations are compelling, yet they also reveal possible exceptions. Occasionally, turbulent flows or asymmetric collapses allow smaller fragments to form. Some models predict that under these rare circumstances, low-mass stars could be born even without metals. Such stars, if they exist, would still be glowing today, hidden among the faintest members of the galactic halo. Observational astronomers have taken up the challenge of searching for these hypothetical survivors. They sift through immense catalogues of stars, identifying candidates based on their colors, brightness, and positions. High-resolution spectroscopy then tests these candidates for signs of metal poverty. A star that shows no detectable iron or carbon becomes a subject of intense scrutiny. The line between almost metal-free and truly pristine is difficult to draw, and so far no confirmed metal-free star has been found. Yet the hunt continues, because the discovery of even one would change everything. The philosophical implications are profound. a confirmed low-mass population, 3 star would be the oldest surviving object in the universe, older than any galaxy, older than any cluster, older than all but the light of the cosmic microwave background itself. It would be a direct witness to the moment when darkness first gave way to starlight. Such a star would embody continuity across nearly 14 billion years, linking the cosmos of the Big Bang to the cosmos of today. Its spectrum would be a relic more ancient than any fossil, carrying information untouched by time. Even in their absence, population 3 stars shaped the trajectory of astrophysics. Their predicted existence drives the design of surveys, the construction of instruments, and the framing of questions. Every new telescope, from the James Webb Space Telescope to the upcoming extremely large telescope, carries with it the hope that the shadows of population 3 may finally be glimpsed. Whether through direct detection of their light in distant galaxies or through the discovery of a true survivor in our halo, the pursuit continues. Meanwhile, the stars we do observe whisper of their presence indirectly. Ultra-metal poor stars with odd abundance patterns serve as the fossils of early supernovae. Their chemical codes are interpreted as the echoes of population 3 deaths, their strange ratios of carbon, magnesium, and iron mapping onto theoretical models of primordial explosions. These fossils are not survivors, but they are witnesses, recording the chaos of the first stellar generations. The paradox is not merely academic. The lives and deaths of population 3 stars shaped the evolution of everything that followed. They determined the timing of reionization, the enrichment of the interstellar medium, the seeds of black holes, and the pathways by which galaxies grew. To understand them is to understand the transition from a simple universe to a complex one, from uniform gas to a cosmos filled with stars, planets, and life. And so the story of population 3 stars brings us to the heart of the mystery. Theory insists they were titans, fleeting, yet transformative. Observation suggests their signatures linger in the most ancient stars, yet no living example has been found. The boundary between theory and evidence is sharpest here, where the universe keeps its secrets most closely guarded. To push further, we must now return to the case studies that ignited this entire debate. The impossible survivors themselves, the ultra-metal poor stars, whose very existence forces us to reconsider whether population 3 stars truly vanished, or whether a few of them remain, faint and unyielding, at the edges of the Milky Way. Among the countless stars that drift in the halo of the Milky Way, a few shine with a kind of defiance. They are faint, ancient, and chemically impoverished, and yet their very existence contradicts the expectations of theory. These are the so-called impossible survivors, stars whose metallicities are so low that by all rights they should not exist. They have become the touchstones of modern astrophysics, each one a puzzle piece that refuses to fit neatly into the established picture of cosmic evolution. The story begins with He 01075240, discovered in the year 2002. When its spectrum was analyzed, astronomers were stunned. Its iron content was measured at roughly 1/200,000th, that of the Sunday. To grasp the extremity of this number, consider that if the sun were melted into a cosmic crucible, a single spoonful drawn from it would contain more iron than exists in the entire star, He 01075240. Such scarcity was not merely surprising, it was unsettling, for it suggested that this star had formed from gas barely touched by previous generations of supernovae. According to the models, such gas should not have produced a low-mass star capable of surviving to the present day, and yet there it was, quietly glowing in the halo. A decade later, in the year 2011, another shock arrived. SDSS J102915+172927 was discovered through the Sloan Digital Sky Survey. Its metallicity was among the lowest ever measured, but what truly set it apart was its lack of carbon and oxygen enrichment. Many theories had proposed that trace amounts of these elements were essential for cooling in the early universe, enabling small stars to form. Without them, the gas clouds should have collapsed only into massive, short-lived stars. The existence of SDSS J102915+172927 therefore struck directly at the heart of the cooling paradigm. The pattern did not end there. In 2013, the star SMSS J031300.36-67083.9.3 was identified by the SkyMapper survey. Its iron content was so low that only an upper limit could be established, making it effectively the most iron-poor star ever observed. The very fact that it could exist challenged the foundations of stellar formation theory. Was it truly formed from pristine gas, or had it somehow shed or diluted its metals over billions of years? No clear answer was forthcoming. Each of these stars presents astronomers with a choice. Either the models of early star formation are incomplete, or the interpretations of stellar spectra are misleading us. Some argue that these stars may not be true survivors from the primordial era, but rather second-generation stars formed from gas enriched by faint supernovae. In such scenarios, the peculiar abundance patterns are explained by unusual explosions that released carbon but trapped iron. Others suggest that accretion may play a role, with stars that began metal-free gradually collecting tiny amounts of metals from the interstellar medium over billions of years. The stakes of this debate are immense. If even one of these stars is confirmed to have formed without metals, then it would be the first direct evidence of a population 3 survivor. It would prove that low-mass stars could indeed form in the primordial universe, and that some of them have lived long enough for us to study today. Such a discovery would rewrite our understanding of the early cosmos. On the other hand, if all of these stars are shown to be second-generation objects, then they remain no less valuable, for they record the chemistry of the first supernovae with extraordinary fidelity. The challenge lies in disentangling these possibilities. Spectroscopy can measure abundances with great precision, but it cannot reveal a star's full history. Kinematic studies with Gaia have shown that many of these stars move on orbits characteristic of ancient halo populations, some even tracing back to disrupted dwarf galaxies. This adds context, but not certainty. The chemistry remains the decisive evidence, and the chemistry is difficult to interpret when the abundances are pushed to such extreme limits. What is beyond doubt is that these impossible survivors are more than anomalies. They are the most valuable fossils in the stellar record, each one a messenger from an epoch otherwise lost to time. Their faint light carries whispers from billions of years ago, challenging our assumptions and reminding us that the universe often refuses to conform to neat categories. As long as they shine, they will keep asking the question that lies at the heart of this mystery. How can a star exist when every model says it should not? The pursuit of answers leads naturally from these case studies into broader theory. If the impossible survivors are real, then star formation in the early universe must have involved processes more intricate than we imagined. Cooling, fragmentation, and enrichment must be re-examined, not in the abstract, but in the specific context of these defiant stars. To follow this trail, we must now step back from individual anomalies and consider how the physics of star formation itself may need to be rethought. The case of the impossible survivors forces us to consider just how much of our theoretical scaffolding might be incomplete. When HE01075240 was first measured, some astronomers speculated that perhaps the readings were mistaken, that the absorption lines were too faint, and the calculations had been misled by noise. But repeated observations with more powerful instruments confirmed the numbers. This was not an error, it was a fact that demanded explanation. The same held true for SDSS J102915+172927 and SMSS J031300.36-6708339.3. They were not illusions conjured by faulty data, they were real stars, and their existence demanded that astrophysics either bend or break. One of the most striking features of these stars is their variety. While each has extremely low metallicity, their chemical fingerprints are not identical. Some show high carbon relative to iron, while others show none at all. Some have detectable magnesium, calcium, or barium, while others seem devoid of nearly everything heavier than helium. This diversity suggests that they did not all form in the same environment or under the same conditions. Rather, they bear the marks of different enrichment histories, as though each were a page torn from a different book of early cosmic events. The idea of faint supernovae has gained traction as one possible explanation. In such explosions, the outer layers of the progenitor star are expelled, while much of the core material, rich in iron, falls back into the remnant. The result is an enrichment of lighter elements without the heavy metals. A second-generation star forming from such material would inherit that peculiar chemistry. This could explain why some of the impossible survivors appear rich in carbon but poor in iron. Yet this does not solve the puzzle entirely, for stars like SDSS J102915+172927 show no such enrichment, existing in defiance of even the faint supernova model. Accretion presents another possible pathway. Over billions of years, a star traveling through the galaxy could sweep up trace amounts of metals from the interstellar medium. Even if it were born metal-free, its atmosphere might gradually become polluted. If this process is real, then some of the impossible survivors could have started as population. 3 stars, but no longer appear pristine. The difficulty lies in quantifying how much material a star can accrete over cosmic time. Models vary, and the results depend heavily on assumptions about the density and motion of the interstellar medium. A more radical idea is that the physics of cooling and fragmentation in the early universe was more flexible than once assumed. Perhaps gas clouds could fragment into smaller clumps without the aid of carbon or oxygen, under conditions influenced by turbulence, magnetic fields, or interactions with dark matter. If so, then low-mass stars could have formed directly from pristine gas, sidestepping the need for enrichment altogether. In this scenario, the impossible survivors may be exactly what they appear to be, genuine relics of the primordial era. The difficulty in distinguishing these possibilities lies not only in the stars themselves, but in the limits of our measurements. When abundances drop to levels thousands of times lower than the Sun, the lines in the spectrum become vanishingly faint. At times, astronomers are not measuring presence but setting upper limits, saying only that if iron exists in the star, it is below a certain threshold. The difference between none and almost none is scientifically significant, but observationally subtle. The line between a second-generation star and a population 3 survivor is therefore blurred, leaving us suspended between possibility and uncertainty. Despite this ambiguity, the scientific community views these stars as treasures. They are the most direct evidence we have of conditions in the early universe. Whether they are true survivors or immediate descendants, they represent the closest approach to the first generation of stars that current instruments can reach. Each new discovery adds another data point, another fragment of the cosmic story. Together, they trace the outline of a chapter that has yet to be fully written. The existence of impossible survivors does not weaken astrophysics, it strengthens it. By exposing the limits of our models, they force refinement and creativity. Science advances not through perfect agreement, but through anomalies that resist easy explanation. These faint stars, scattered across the halo and beyond, are the anomalies that keep astrophysicists awake at night, rethinking equations, running new simulations, and questioning assumptions once held as firm. And so the impossible survivors serve as both puzzle and promise. They promise that the universe holds secrets still hidden in plain sight, that even the faintest points of light can overturn our deepest assumptions. They puzzle us by standing where they should not, shining in defiance of theory. To understand them fully, we must follow their challenge into the very core of stellar physics, asking how stars form, how gas cools, and how theory must adapt to accommodate the evidence of these quiet rebels. The impossible survivors have become more than individual curiosities. They are now the cornerstones of an unfolding narrative that reaches across theory, observation, and even philosophy. Each of them, faint and unassuming to the eye, becomes a battlefield where models of cosmic history are tested against the stubborn facts of reality. Their stories reveal just how much of science is shaped not by the patterns that fit neatly into equations, but by the exceptions that resist categorization. Consider again J102915+172927. When its spectrum first showed the signature of iron at a level 1/200,000th that of the Sun, it was as though a window had been opened onto a world no one thought could exist. The star itself is not luminous or dramatic, but the silence of its spectrum spoke louder than the light of the brightest galaxy. In the gaps where iron lines should have been, astronomers saw not absence but possibility, a reminder that the universe does not conform to our expectations simply because they are elegant. The case of SDSS J102915+172927 pushed this reminder even further. Without the enrichment of carbon and oxygen that theory suggested was essential for cooling, the star seemed to have emerged from nothing but hydrogen and helium. If this interpretation is correct, then it stands as proof that small stars can indeed form in environments that theory had long declared barren. To admit this possibility is to loosen the grip of certainty and embrace a universe that is more inventive than we had imagined. SDSS J102915+172927, the faintest whisper of iron yet observed, extends the pattern still further. Each of these discoveries stretches the boundaries of plausibility, and together they form a constellation of contradictions. They are not outliers to be ignored. They are the essential data points that redefine the curve. What emerges from these studies is not despair, but a recognition of how science grows. Models of stellar formation that once seemed unshakable are now being revised to include the effects of faint supernovae, exotic cooling pathways, and even the subtle influence of turbulence in primordial gas clouds. Simulations now attempt to replicate the diversity seen in these stars, exploring scenarios where low-mass survivors can indeed arise. Every new parameter, every added complexity, is not a concession of failure, but an expansion of understanding. The impossible survivors also embody the human side of astronomy. For the scientists who dedicate years to studying them, these stars are not merely points of data, they are companions on a journey into the unknown. Long nights spent gathering photons from faint halos, long days spent analyzing spectra line by line, all serve a purpose greater than the sum of the numbers. Each spectrum is a dialogue with the universe, each absorption line a message carried across more than 13 billion years. To read that message is to commune with history on a scale that dwarfs human experience. Their significance extends beyond astrophysics. The question of whether truly metal-free stars still exist is not just technical, it touches on our deepest sense of place in the cosmos. If even one such star survives, then it is older than any other object we can see with our eyes, a direct witness to the dawn of creation. Its light would be a bridge across nearly all of cosmic time, a reminder that in the vastness of the universe, some stories are still unfolding in front of us. If none survive, then the impossible survivors we do see become even more precious, for they are the nearest we can come to touching that ancient epoch. In either case, the lesson is the same. The universe is not a finished story, but an evolving one, written in the language of physics, but full of unexpected turns. The impossible survivors remind us that the cosmos is not beholden to our predictions. Instead, it invites us to revise, to question, and to marvel. Their faint light, barely strong enough to reach us, carries not just the imprint of ancient chemistry, but the challenge to keep looking deeper. As this chapter closes, the question lingers in the air: how can stars exist when every model insists they should not? To answer, we must step beyond the case studies and confront the physics itself. If our models of star formation cannot account for these anomalies, then perhaps the models must change. The path ahead leads into the heart of theory, where astronomers seek to rethink the mechanisms of cooling, fragmentation, and survival in the earliest epochs. Only by revisiting the very process of star birth can we hope to resolve the riddle posed by these survivors of the impossible. The impossible survivors force us to reconsider the very physics of how stars are born. For decades, the narrative was straightforward. In the early universe, gas composed only of hydrogen and helium could not cool efficiently, so it collapsed into massive stars that lived briefly and died violently. Only after those stars exploded and seeded space with heavier elements could smaller, long-lived stars form. This story was neat, logical, and elegant. Yet the faint halo stars with vanishingly small metallicity tell us the cosmos did not follow such a simple script. To understand how theory is being reshaped, we must look closely at the role of cooling in star formation. Cooling is the process by which gas loses energy, allowing gravity to overcome pressure and drive collapse. Without cooling, gas clouds remain too hot and diffuse to fragment into stars. In the early universe, with no carbon or oxygen to radiate energy efficiently, the only coolant available was molecular hydrogen. But hydrogen is a poor radiator, and it limits how small the collapsing fragments can become. This is why early simulations predicted stars with masses tens or even hundreds of times greater than the Sun. Yet the existence of low-mass, ultra-metal-poor stars suggests that something else was at work. One candidate is dust. Even the tiniest grains of solid material, formed in the ejecta of the first supernovae, can dramatically enhance cooling. Dust provides surfaces on which molecules can form, and it radiates energy at wavelengths different from gas, creating new pathways for energy to escape. If faint supernovae produced enough dust, then small stars could form in gas clouds enriched at even the most minimal levels. This would mean that the impossible survivors are not truly primordial, but second-generation stars born in the immediate aftermath of the first stellar deaths. Another possibility lies in the chemistry of carbon and oxygen. These elements, even in trace amounts, open up new cooling channels through their atomic transitions. Some ultra-metal-poor stars show enhancements in carbon, hinting that their birth clouds were enriched just enough to allow efficient cooling. In such scenarios, the threshold for low-mass star formation may be far lower than once assumed. A cloud with only 1/10,000th the metallicity of the Sun might still be able to fragment into stars as small as the ones we observe today. Theorists have also begun to explore the role of turbulence. In the chaotic flows of collapsing gas, pockets of higher density can form, creating localized conditions where cooling is more effective. These pockets may fragment independently, leading to smaller stars than average. Magnetic fields, though weak in the early universe, could also influence the process by channeling gas flows and altering the dynamics of collapse. Each of these factors complicates the once simple picture, replacing it with a more intricate tapestry where multiple pathways to star formation coexist. Computational simulations have become essential in exploring these ideas. Using supercomputers, astrophysicists can model the evolution of gas clouds under different assumptions about cooling, dust, turbulence, and enrichment. The results often reveal surprises. In some runs, gas fragments into a handful of massive stars, as expected. In others, a spectrum of masses emerges, including stars small enough to survive billions of years. These outcomes depend sensitively on initial conditions, reminding us that the universe may have been less uniform than the average model suggests. What is most striking about this rethinking is the humility it imposes. For years, the field assumed that population 3 stars were all giants, destined to burn fast and die young. Now we must admit that the cosmos may have been more versatile. The laws of physics allowed more diversity than we recognized, and the survivors we see today are evidence of that flexibility. The neat categories of population 3, population 2, and population 1 may blur at the edges, with stars existing along a continuum rather than in rigid classes. The story of rethinking star formation is not just about technical adjustments. It is a reminder that the universe is not obligated to match our expectations. Every faint spectrum that resists explanation is an invitation to revise our models, to look for overlooked processes, and to embrace complexity. The impossible survivors do not diminish our theories, they refine them. They transform a tidy story into a richer and more accurate one, where dust, turbulence, and exotic supernovae all play roles. As these ideas evolve, they connect to broader questions about the structure of the Milky Way itself. If low-mass stars could form in the earliest epochs, then some of the halo stars we see today are not just old, they are fossils of processes that reshaped galaxies. To trace their origins, we must consider not only how stars form, but also where they end up. This leads us naturally from the physics of individual stars to the archaeology of the galactic halo, where the survivors of ancient times still drift, carrying with them the memory of cosmic beginnings. The rethinking of star formation in the early universe has unfolded as a dialogue between evidence and imagination. On one side stand the models, with their equations of gravity, thermodynamics, and radiation transport. On the other stand the faint halo stars, whose spectra are stubborn reminders that the models do not yet tell the full story. This conversation is not adversarial but constructive, a constant refinement of our understanding as new data emerges. One of the central shifts in this dialogue is the recognition of thresholds. For years, theorists assumed that without metals, small stars could not form. But observations of ultra-metal-poor stars have led to the idea of a critical metallicity, a tipping point where even the tiniest trace of heavy elements can unlock efficient cooling. This threshold may be as low as 1/10,000th of the solar metallicity. Below that, gas clouds produce only giants, but above it, even slightly, fragmentation into low-mass stars becomes possible. If this is correct, then the impossible survivors are not contradictions at all, but confirmations that the threshold is far lower than once assumed. The faint supernova hypothesis provides a natural explanation for how this enrichment occurred. When the first massive stars died, some of them may have exploded weakly, releasing their outer layers rich in carbon and magnesium, while retaining their iron in the remnant. The surrounding gas clouds would then have been seeded with precisely the elements needed to cool efficiently. Stars forming from this material would appear extremely metal-poor by iron standards, but enriched in lighter elements. Their chemistry would carry the imprint of these unusual deaths, and indeed, many of the stars studied today display such patterns. Dust has also emerged as a key player. Laboratory experiments and theoretical studies suggest that even in the first supernovae, dust grains can condense and survive. These grains, tiny solids of carbon, silicates, or other compounds, act as powerful radiators, allowing gas to shed heat much more effectively. Dust also serves as a catalyst for molecular hydrogen formation, further enhancing cooling. The presence of even a small amount of dust could therefore have enabled the formation of low-mass stars in the very first generations. The possibility of fragmentation adds another dimension. Gas clouds are not smooth and uniform. They are turbulent seas where eddies and shocks create pockets of higher density. In these pockets, cooling can be more effective, leading to the birth of smaller stars, even when the average conditions favor massive ones. Modern simulations that incorporate turbulence show a wide range of stellar masses emerging, hinting that the early universe may have been more diverse than the clean models once predicted. Magnetic fields, though weak, may have contributed as well. Even small primordial fields could influence the collapse of gas by channeling flows and altering angular momentum. This could slow collapse in some regions and hasten it in others, creating the variety of conditions necessary for different outcomes. The details remain uncertain, but the possibility adds richness to the picture, reminding us that no single factor tells the whole story. Each of these mechanisms points to the same conclusion: the early universe was not a sterile arena where only giants could be born. It was a complex environment where multiple processes intersected, sometimes producing massive stars that lived briefly, sometimes producing smaller ones that could endure. The ultra-metal poor stars we see today may therefore be survivors of this complexity, their existence not impossible, but inevitable once we expand our understanding. The rethinking of star formation also has consequences beyond stellar physics. If low-mass stars could form earlier than expected, then galaxies may have assembled differently. Small stars live far longer and provide stability to stellar populations. Their presence in the earliest epochs would alter the timeline of enrichment, the pace of reionization, and the growth of galactic structure. This means that every faint halo star carries not just a personal story of survival, but a cosmic story of how galaxies evolved from simplicity to grandeur. As we confront these revised models, one theme emerges clearly: the universe is more inventive than our equations. It finds pathways to outcomes we had declared forbidden. It produces survivors we had declared impossible. The lesson is not one of failure, but of humility. For in expanding our theories, we come closer to truth. The impossible survivors become not contradictions but guides, pointing us toward the processes that truly shaped the early cosmos. The next step is to place these survivors within the grand architecture of the Milky Way. They are not isolated curiosities, but members of a larger family, drifting in the galactic halo, globular clusters, and even in dwarf galaxies. Their locations and motions preserve clues about the history of the galaxy itself. To understand their significance fully, we must see them not only as individuals, but as fossils embedded in the larger structure of the Milky Way, relics of a time when the galaxy was still assembling from smaller fragments. The effort to rethink star formation does more than adjust theories of how individual stars came to be. It compels us to reconsider how the galaxy itself was assembled, because stars are not scattered randomly, but born in groups, embedded within larger structures. The survival of ultra-metal poor stars across billions of years tells us that their birthplaces were not destroyed entirely, but that fragments of those environments linger within the halo of the Milky Way. Each star is a fossil, but together they form a fossil record of galactic history. The halo, that vast spherical region surrounding the disk of the Milky Way, is home to many of these survivors. Unlike the younger, metal-rich stars of the disk, the halo population is dominated by ancient stars with low metallicity. Their presence there is no accident. The halo is a graveyard of past mergers, a place where the remnants of dwarf galaxies and globular clusters have been scattered by the gravitational tides of the Milky Way. The chemistry and motion of the halo stars therefore encode not just the story of their own formation, but the story of how the galaxy grew through countless collisions and accretions. In this light, the impossible survivors are not solitary mysteries, but members of a larger community. Some of them trace orbits that carry them far above and below the disk, plunging through the galaxy in elongated paths that betray their ancient origins. Others move in streams, the remnants of disrupted dwarf galaxies, torn apart by the Milky Way's gravity. These motions, mapped with exquisite precision by the Gaia mission, reveal that the halo is not a random cloud of stars but a dynamic archive, each orbit a page in the story of galactic assembly. By combining chemistry with kinematics, astronomers can reconstruct the events that shaped the Milky Way. A star enriched in carbon but poor in iron, moving on an orbit consistent with capture from a dwarf galaxy, tells of a faint supernova in a small system that was later swallowed by the Milky Way. Another star, with similarly low metallicity but a different abundance pattern, might trace back to a separate merger event. In this way, the halo becomes a patchwork of histories, stitched together by the motions and compositions of its stars. Globular clusters add another piece to this puzzle. These dense spherical groups of stars orbit the Milky Way as relics of ancient formation events. While most globular clusters are more metal-rich than the most extreme halo stars, some harbor populations that are nearly as old and primitive. They show that environments existed where large numbers of stars formed in the early universe, some of which may still harbor survivors from those first epochs. The clusters act as time capsules, preserving chemical signatures that would otherwise be diluted by the mixing of the galactic disk. The rethinking of star formation also informs the search for these survivors in other galaxies. If faint supernovae, dust, and turbulence could enable low-mass star formation in the Milky Way's progenitors, then the same should be true for dwarf galaxies orbiting us today. Indeed, surveys of the Sculptor and Fornax dwarf galaxies have revealed stars with metallicities nearly as low as those in our own halo. These discoveries extend the reach of stellar archaeology, showing that the processes we infer were not unique to the Milky Way, but part of a universal story. All of these strands converge on a single insight. The early universe was not uniform, and star formation was not governed by a single rule. It was a chaotic and fertile epoch, producing giants that lived fast and died, but also producing smaller stars that endured. The impossible survivors are the evidence of this diversity, their light still burning billions of years later. They are proof that the universe found ways to create longevity even in its earliest days. The task now is to integrate these insights into a coherent framework. Theories must account not only for the giants of population 3, but for the survivors we see today. Observations must continue to push the limits, seeking ever fainter and purer stars. And simulations must incorporate the complexities of dust, turbulence, and faint supernovae, revealing the pathways by which the impossible became reality. As this chapter of rethinking draws to a close, we see the outlines of a richer narrative. The universe did not march in a straight line, from primordial simplicity to modern complexity. It wandered, experimented, and produced outcomes that surprise us still. The survivors in the halo are not contradictions, but companions, urging us to expand our vision of what is possible. To follow their guidance, we must now turn fully to the galactic halo itself, treating it as the fossil bed of cosmic history, where the deepest truths of star formation and galactic assembly remain waiting to be uncovered. The halo of the Milky Way is a realm of quiet persistence, a vast and sparsely populated sphere that surrounds the bright disk where most of the galaxy's stars reside. To the casual eye, it is invisible, for its stars are faint and scattered, but to astronomers, it is one of the most important structures in the cosmos. The halo is the graveyard of galactic history, a place where the oldest stars drift, carrying within their light the record of events that occurred more than 13 billion years ago. To study the halo is to walk among fossils, not of bones or shells, but of ancient starlight, frozen since the dawn of time. The halo differs strikingly from the disk. While the disk is rich in metals and filled with young stars orbiting in ordered circles, the halo is sparse, diffuse, and chaotic. Its stars travel on elongated and tilted orbits, plunging through the galaxy like comets. Many of them are old beyond easy comprehension, survivors from an era when the Milky Way itself was still forming. Their metallicities are often far lower than those of disk stars, marking them as members of the earliest generations to emerge after the first supernovae seeded the universe with heavy elements. One of the most profound insights of modern astronomy is that the halo is not a uniform structure but a mosaic. Its stars come from many sources, stitched together by the gravitational tides of the Milky Way. Some were born in the galaxy itself, in its earliest gas clouds. Others were captured from dwarf galaxies that were swallowed long ago, their stellar populations stretched into streams across the sky. Still others may have originated in globular clusters, the dense spherical star groups that orbit as relics of ancient times. Each star is a clue, but taken together, they reveal a picture of relentless growth through accretion and merger. Gaia has revolutionized our view of this fossil record. By measuring the positions and motions of more than 1 billion stars, it has shown that the halo is not a random scattering, but a layered history of galactic events. One of the most famous examples is the Gaia sausage, a population of stars with shared orbital properties that betray their origin in a single massive dwarf galaxy devoured by the Milky Way billions of years ago. The chemistry of these stars matches their kinematics, confirming that they came from outside and now drift as relics of a vanished system. Among these relics lie the impossible survivors, the ultra-metal poor stars that bear the signatures of the earliest epochs. Their orbits carry them far into the outer halo, beyond the disk and bulge, where the density of stars is low and the night sky is nearly empty. From these remote vantage points, they shine faintly, untouched by the processes that enriched the disk with metals. Their light is pure testimony from a time before the Milky Way had grown to its present majesty. Globular clusters add another layer to the fossil record. These dense assemblies of hundreds of thousands of stars orbit the galaxy as if frozen in time. Many of them are nearly as old as the universe itself, dating back more than 12 billion years. While they are not as metal poor as the most extreme halo stars, they still represent some of the earliest environments where star formation occurred. Their stars often share similar abundances, suggesting that they formed together in massive bursts of star formation. As such, globular clusters are not just relics, they are laboratories where the physics of early star formation can still be studied directly. The halo also contains stellar streams, faint rivers of stars that trace the paths of disrupted dwarf galaxies and clusters. These streams are fossils in motion, their elongated arcs across the sky showing where gravity has stretched their original systems into ribbons. By mapping these streams, astronomers can reconstruct past mergers and understand how the Milky Way assembled itself. Many of the stars within them are ancient and metal poor, extending the fossil record into structures that can be traced and measured. The concept of stellar fossils is more than metaphor. Just as paleontologists reconstruct ancient ecosystems from the bones of long-dead creatures, astronomers reconstruct cosmic history from the spectra and motions of halo stars. The age distribution, the metallicities, the abundance patterns, and the orbital properties all combine to tell a story of growth, enrichment, and survival. Each star is an individual relic, but together they are the remains of galaxies consumed, clusters preserved, and processes long past. The halo is not static. Its stars continue to orbit, streams continue to stretch, and new mergers continue to occur. Yet in its vastness, the memory of the early universe remains preserved more faithfully than in the crowded, dynamic disk. It is here that the closest approach to the first stars may still be found, and it is here that the chemical and dynamical fossils of the Milky Way remain for us to study. To recognize the halo as a fossil bed is to recognize that our galaxy is not a single entity, but a collection of histories. Each star in its diffuse reaches is a survivor, bearing silent witness to the dawn of starlight. To follow this trail is to step beyond the narrow question of how individual stars form and into the broader question of how entire galaxies are assembled. And so the impossible survivors, embedded within the halo, lead us from stellar archaeology into the realm of galactic archaeology, where the past is written across the sky, in the motions and compositions of ancient stars. The idea of the halo as a fossil bed becomes clearer when we consider how stars arrived there. Unlike the disk, which is a relatively calm and ordered structure, the halo is chaotic because it was built from many pieces. Small galaxies, drawn in by the Milky Way's gravity, were torn apart and scattered. Their stars, once bound together, now move independently along stretched and twisted orbits. Each captured system left behind a trail, and these trails overlap to form the diffuse sphere of the halo we see today. In this sense, the halo is less a single structure than a vast archive of galactic mergers. The most compelling evidence for this assembly comes from stellar streams. These delicate rivers of stars stretch across the sky, invisible to the naked eye, but revealed by careful mapping. They are the remnants of dwarf galaxies and globular clusters pulled apart over billions of years. One of the most famous, the Sagittarius Stream, winds around the Milky Way in a looping path, marking the slow consumption of the Sagittarius dwarf galaxy. By studying the motions and chemistry of these streams, astronomers can reconstruct the history of accretion events, much as geologists reconstruct the shifting of continents. Within these streams, ancient stars serve as messengers of their original systems. Their metallicities and abundance ratios preserve the chemical environment of their birthplaces. A stream rich in carbon but poor in iron might trace back to a dwarf galaxy where faint supernovae dominated. Another, with higher magnesium, might reflect a different enrichment history. The stars may now be scattered, but their chemistry binds them together, revealing their shared origins even when their paths diverge across the sky. Globular clusters add to this fossil record with a different kind of testimony. Unlike dwarf galaxies, which can have varied star formation histories, globular clusters are snapshots of single bursts of formation. They formed in great numbers more than 12 billion years ago, when the universe was still young. Many orbit far into the halo, stable despite the passage of time. Their stars are uniform in age and often similar in chemistry, making them laboratories for studying the physics of early star formation. They show that the galaxy was capable of creating dense, massive star systems very early, and their survival demonstrates the resilience of structures forged in the first billion years after the Big Bang. The halo is not only a museum of stellar fossils, it is also a stage where the gravitational architecture of the Milky Way can be probed. The paths of halo stars respond to the pull of dark matter, the unseen mass that outweighs visible matter by a factor of 5. By mapping their orbits, astronomers infer the distribution of dark matter throughout the galaxy. In this way, the fossils of the halo are not just records of the past, they are tools for understanding the present, revealing the hidden structure that holds the galaxy together. Some of the most exciting discoveries have come from combining chemistry and motion. Gaia has shown that groups of stars with common orbits often share common abundance patterns. These chemical signatures act like surnames, linking stars to their ancestral systems. One group, for example, may all carry the chemical imprint of a faint supernova, while another shows the pattern of more energetic explosions. By tying these chemical surnames to orbital families, astronomers can reconstruct not only where stars came from, but also the physical conditions that shaped their birth. The halo extends far beyond what we can easily see. Its outer reaches stretch hundreds of thousands of light years into space, populated by stars so faint they are barely detectable. These outer halo stars are particularly valuable because they are less likely to have been contaminated by later enrichment. Their metallicities are often the lowest of all, making them prime candidates for containing the impossible survivors. Searching these remote regions is difficult, but the rewards are immense, for they bring us closer to the conditions of the earliest star formation. The picture that emerges from all of this is one of dynamic complexity. The Milky Way is not a closed system, but an open one, shaped by interactions, mergers, and accretions over billions of years. The halo preserves the evidence of these events in a way the disk cannot. Its stars are fossils not because they are static, but because they retain the memory of environments that no longer exist. They are the bones of devoured galaxies, the ashes of primordial explosions, the survivors of epochs when the cosmos was still young. To study them is to read a history book written in light, one that stretches from the first stars to the present. Each halo star adds a line, each stream a chapter, each globular cluster a paragraph. Together, they tell a story of growth through struggle, of a galaxy built from fragments, of survival against the odds. The impossible survivors are part of this story, not anomalies but essential pages, showing that even in the earliest times, the seeds of endurance were sown. As we turn deeper into this record, the questions grow larger. If the halo is the fossil bed of galactic history, then what does it reveal about the limits of our models? How do we reconcile the stubborn facts of ultra-metal-poor stars with the assumptions of stellar physics? To follow this thread, we must step from the fossils themselves to the frameworks we use to interpret them, confronting the cracks that appear in our models when faced with the evidence of stars that should not exist. The halo's importance as a fossil record lies not only in the stars it contains, but in what those stars force us to confront about the galaxy's origins. When astronomers map the metallicities of halo stars, they see a distribution that falls off steeply at the lowest values. Most halo stars are already enriched compared with the impossible survivors, yet the tail of the distribution extends into metallicities so low that they resemble the universe before enrichment had truly begun. These rare stars are the needles in the galactic haystack, and each one redefines the limits of what star formation in the early universe must have been capable of producing. The diversity of these fossils reveals that the halo is a layered structure. Its inner regions contain stars with moderately low metallicity, likely formed within the Milky Way itself during its earliest epochs. The outer halo, by contrast, is dominated by stars thought to have been accreted from dwarf galaxies. These stars are older, poorer in metals, and often follow irregular orbits that carry them far from the galactic center. Their chemistry reflects slower enrichment histories, typical of smaller systems with fewer supernovae. In this way, the halo acts like a stratified archive, with each layer recording a different stage of galactic assembly. Stellar archaeology in the halo has also revealed surprises about the nature of enrichment itself. Some stars show unusual ratios of heavy elements, suggesting that not all supernovae contributed equally to the chemical evolution of their environments. In some cases, the abundance patterns point to rare processes such as neutron star mergers, which can create elements heavier than iron. That such patterns are found in the halo underscores its role as a repository not only of common events, but of the rarest and most exotic phenomena in cosmic history. The outermost reaches of the halo remain largely unexplored, yet they hold enormous promise. Stars in these distant regions are so faint that only the largest telescopes can study them in detail. Their isolation makes them particularly valuable, for they are less likely to have been contaminated by multiple generations of enrichment. They may therefore preserve the clearest signatures of the first supernovae. Ongoing and future surveys, using instruments such as the Vera-Rubin Observatory, will expand our census of these stars dramatically, offering new opportunities to uncover fossils from the very dawn of starlight. The recognition of the halo as a fossil bed has transformed how astronomers think about the Milky Way. It is no longer viewed simply as a majestic spiral galaxy, but as the culmination of countless mergers, each leaving behind remnants in the form of stars, streams, and clusters. The halo is the evidence of these events, a silent witness to billions of years of cosmic evolution. Without it, the story of the galaxy would be incomplete. With it, the galaxy becomes not a static structure, but a living history, written across the sky, in faint, ancient points of light. For the impossible survivors, the halo is both cradle and refuge. It is where they were born, in environments scarcely enriched by the first explosions, and it is where they remain, untouched by the bustling cycles of the disk. Their presence there is not accidental but necessary, for only in the low-density reaches of the halo could such stars endure without being swept into new waves of star formation. They are not merely old stars, they are time capsules, carrying within them the imprint of a universe just beginning to awaken. The lessons of the halo are clear. By treating it as a fossil bed, astronomers have uncovered the processes by which galaxies grow, the diversity of early star formation, and the resilience of stars that should not exist. The fossils it contains are not inert. They are active guides, pointing us toward the gaps in our theories and the frontiers of our knowledge. The halo is not just a relic of the past, it is a laboratory for the present, where every new discovery reshapes the map of cosmic history. And yet, even as the halo provides answers, it also sharpens the questions. How do the abundance patterns of its most extreme stars fit into our models of nucleosynthesis? Why do some of its fossils show evidence of processes that should have been vanishingly rare in the early universe? Most pressing of all, how do we reconcile the presence of the impossible survivors with the certainty that population 3 stars should not have lived long enough to reach us? These cracks in the models demand attention, for they are the pressure points where science moves forward. Thus, the journey from observation to understanding leads us from the fossils of the halo into the challenges they pose. To make sense of them, we must examine the foundations of our theories, testing the assumptions and limits of stellar evolution itself. The cracks in the models may not be flaws but openings, windows into a deeper truth about the cosmos. To explore them is to take the next step in our pursuit of the stars that should not exist. Science thrives on the cycle of prediction and correction. A theory takes shape, guided by mathematics and physical laws. Then observation steps in to test its boundaries. When the two agree, confidence grows. When they diverge, the cracks that appear are not failures, but invitations to deeper understanding. In the case of the earliest stars, those cracks have become unmistakable. The existence of ultra-metal-poor stars, the chemical fossils of the halo, and the impossible survivors together expose the weak points in the models we have long relied upon. At the heart of these models is stellar evolution, the framework that explains how stars are born, live, and die. The equations describe how nuclear fusion transforms hydrogen into helium and heavier elements, how energy moves outward, through radiation and convection, and how pressure balances gravity to hold a star stable. These models have been tested against countless observations of ordinary stars and have succeeded brilliantly in explaining much of what we see. But their assumptions become less certain when pushed into the extremes of the early universe. One of the cracks lies in the treatment of nuclear reaction rates. Fusion depends on the probabilities of atomic nuclei colliding and sticking together, probabilities that are measured in laboratories and then extrapolated to stellar interiors. While these rates are well constrained for the temperatures and densities found in stars like the Sun, they are far less certain for the exotic conditions inside massive population, 3 stars, or in the remnants of faint supernovae. Even small uncertainties in these rates can lead to large differences in the predicted abundances of elements. This means that when we compare the chemistry of halo fossils to theoretical yields, mismatches may reflect gaps in nuclear physics as much as in astrophysics. Another source of uncertainty is the modeling of stellar atmospheres. When astronomers derive abundances from spectra, they rely on theoretical models of how light interacts with atoms in the outer layers of stars. These models often assume equilibrium, smooth layers, and one-dimensional structures, but real stars are turbulent, three-dimensional, and far from equilibrium. The convection of gases, the presence of magnetic fields, and the movement of shock waves all influence the strengths of spectral lines. Simplifying these complexities introduces errors, especially when dealing with stars at the very edge of detectability. Simulations of star formation in the early universe also face challenges. They must span scales from the vastness of galactic halos to the fine detail of collapsing gas clouds, a range so large that compromises are inevitable. Approximations about cooling, turbulence, and fragmentation shape the results, and different codes sometimes produce different outcomes. This is not a sign of failure, but a reminder of how difficult it is to model reality when so many processes interact. The existence of ultra-metal-poor stars forces these simulations to confront conditions they did not originally account for, stretching them into new territory. Perhaps the most striking crack is the tension between observation and expectation. Theory predicted that no low-mass, metal-free stars should exist today. Observation has revealed stars with metallicities so low that they approach that boundary. Whether they are truly primordial or merely second generation, their presence challenges the neat division between what is possible and what is not. This is not a small discrepancy, but a fundamental one, for it questions the very processes by which the first stars formed. Astronomy is full of such moments. The orbit of Mercury once defied Newton's laws, until Einstein's theory of general relativity resolved the anomaly. The spectrum of the night sky once hinted at unknown radiation, until the discovery of the cosmic microwave background confirmed the Big Bang. In the same way, the impossible survivors may be the anomaly that points the way to the next leap in our understanding of the cosmos. The cracks in the models are not weaknesses to be ignored, they are clues to be followed. These cracks also serve as reminders of the iterative nature of science. Models are not final truths, but evolving approximations. They succeed where they have been tested, and falter where new evidence emerges. The halo fossils are precisely the kind of evidence that demands revision. Their light tells us that the early universe allowed pathways we did not anticipate, that cooling, enrichment, and star formation were more varied than we thought. The task now is to refine our models to reflect this complexity, closing some cracks while leaving room for the unknown. The next step in this refinement is to look beyond the Milky Way. If our models are to be tested fully, they must account not only for the fossils in our own halo, but also for those in other galaxies, the dwarf galaxies that orbit us, the ancient systems revealed by the James Webb Space Telescope, and the structures probed by future observatories, all provide laboratories where the cracks may widen or narrow. By stepping outside our home galaxy, we expand the scope of the test, placing our theories under the scrutiny of the broader universe. The cracks in the models widen when we confront how simplifications shape our vision of the cosmos. Every model begins with assumptions meant to make the mathematics solvable. For stellar evolution, these include smooth, layered atmospheres, perfectly mixed interiors, and idealized reactions. For cosmological simulations, they include uniform initial conditions, average cooling efficiencies, and simplified treatments of turbulence. Such assumptions are reasonable for gaining a first-order picture, but they become fragile when tested against the edge cases represented by ultra-metal-poor stars. Consider convection, the boiling motion of gases within a star. In real stars, convection creates three-dimensional patterns that affect both the temperature and the distribution of elements in the atmosphere. Yet many models treat convection in one dimension, using approximations that blur out the details. When abundance measurements rely on these models, subtle differences in line strengths can translate into large errors in inferred metallicity. A star that appears to have 1 part in 100,000, the iron of the Sun, may, in reality, have a slightly different ratio, but at such extremes, the distinction is crucial. Non-equilibrium effects add further complexity. Atoms in stellar atmospheres do not always populate their energy states in perfect balance. Collisions, radiation fields, and turbulence can all drive departures from equilibrium, altering the absorption lines we see. Correcting for these effects requires intricate calculations, and even then, uncertainties remain. These corrections can shift abundance measurements significantly, sometimes enough to change whether a star is classified as an impossible survivor or merely an ordinary metal-poor star. On the scale of entire galaxies, simulations must grapple with the interplay of gravity, gas dynamics, radiation, and feedback from supernovae. These processes operate simultaneously and influence each other in non-linear ways. A single assumption about how efficiently gas cools can change whether a simulation produces only massive stars or a mixture that includes low-mass survivors. Similarly, the treatment of feedback from supernovae can determine whether enrichment is uniform or patchy. Observations of halo fossils suggest patchiness, with some stars enriched by faint explosions and others by more energetic ones. Yet reproducing this diversity in simulations remains a formidable challenge. The cracks are also philosophical. Models thrive on simplicity because simplicity can be calculated and compared. But the universe is not obliged to be simple. It may well be that the early cosmos was messier than our equations anticipate, producing outcomes that resist neat categorization. The diversity of ultra-metal-poor stars, with their varying abundance patterns, is evidence of this messiness. Each star seems to tell a slightly different story, as though the universe experimented with many pathways before settling into the patterns we recognize today. Astronomers are not blind to these cracks. Far from weakening the field, they energize it. Every mismatch between model and observation is a chance to refine assumptions, to build more sophisticated simulations, to question what was once taken for granted. This process is not linear. Old ideas are revised, new ones tested, and often the truth lies in a synthesis that no one anticipated. The impossible survivors are therefore not problems to be explained away, but opportunities to expand the boundaries of astrophysics. The response to these cracks has been one of innovation. New generations of simulations now incorporate three-dimensional models of stellar atmospheres, non-equilibrium effects, and more realistic treatments of turbulence and feedback. Observational campaigns target stars across the halo and in dwarf galaxies, building larger samples that reveal patterns invisible in smaller datasets. The James Webb Space Telescope offers glimpses of galaxies so distant that they may contain direct signatures of population. 3 stars, testing whether our revised models hold up beyond the Milky Way. The cracks in the models, then, are not failures, but signs of vitality. They show that our theories are alive, growing in response to the evidence. They remind us that science is a conversation, not a decree. The stars that should not exist are not just anomalies, they are participants in that conversation, asking questions that force us to think harder, calculate more carefully, and look deeper. As we follow this conversation outward, we see that the Milky Way is not the only laboratory. The surrounding dwarf galaxies, faint and ancient, hold their own populations of metal-poor stars. They too are fossils, preserved in environments less disturbed than our own. To continue testing the models, we must turn our gaze outward, beyond the familiar halo, to the wider stage where the universe has kept its oldest records intact. The persistence of cracks in our models underscores a larger truth about the practice of science. No theory is final. Each is a provisional map, useful for navigating reality, but never identical to reality itself. The history of astronomy is filled with maps that guided explorers well until they met the shoreline of the unknown, where anomalies forced them to redraw the contours. The impossible survivors are such anomalies, faint beacons at the edge of knowledge demanding that the map be revised. One of the most persistent cracks concerns the distribution of stellar masses at birth, known as the initial mass function. For present-day star-forming regions, this function is well studied. It shows that low-mass stars are far more common than high-mass ones. But in the early universe, models predicted a very different distribution, skewed toward massive stars. The discovery of low-mass, ultra-metal-poor stars calls this prediction into question. Perhaps the initial mass function was not so radically different in the beginning. Perhaps the universe has always been capable of producing long-lived dwarfs, even under primitive conditions. If so, our picture of early cosmic history must be rebalanced. Another unresolved issue is the diversity of chemical fingerprints. If early enrichment came from only a handful of supernovae, why do we see such a variety of abundance patterns in the halo fossils? Some stars appear enriched in carbon, others in magnesium, still others in neutron, capture elements like strontium or barium. This suggests that the first explosions were not uniform events, but a spectrum of outcomes, from faint collapses to pair instability detonations. Reproducing this diversity in models requires a more nuanced understanding of stellar deaths than we currently possess. Even the nature of dark matter enters into these cracks. The formation of the first stars took place within halos of dark matter, whose gravity drew gas together. The properties of dark matter, whether it is cold, warm, or self-interacting, affect how these halos formed and how gas cooled within them. If our assumptions about dark matter are incomplete, then our models of early star formation inherit that flaw. In this way, the impossible survivors may not only test stellar physics but also the physics of the unseen matter that dominates the cosmos. The role of feedback remains another open question. Supernovae do not simply enrich their surroundings, they also blast gas away, heating and dispersing it. How far this feedback extended, how quickly gas fell back to form new stars, and how patchy the enrichment became, are still uncertain. Observations of halo fossils suggest that feedback was uneven, producing pockets of enriched and unenriched gas side by side. Simulations struggle to capture this patchiness, smoothing over the fine details that may hold the key to understanding the survivors. What is clear is that our models must evolve. Just as the orbit of Mercury once demanded a new theory of gravity, so too do the impossible survivors demand new approaches to early star formation. The cracks are not embarrassments, but opportunities. They show us where to look, where the assumptions fail, and where discovery awaits. They remind us that the cosmos is not obliged to conform to our expectations, that its creativity exceeds our imagination. The stars that should not exist are therefore not outliers to be dismissed, but teachers to be heeded. They highlight the limits of our equations, the fragility of our assumptions, and the necessity of humility. They are the compass points by which the next generation of theories will be oriented. Already, new models are emerging that embrace dust cooling, turbulence, faint supernovae, and even exotic dark matter scenarios. These models do not close the cracks but build bridges across them, offering pathways to explanations that encompass the diversity we observe. And yet, the most powerful test of these models will not come from within the Milky Way alone. The universe offers us countless other laboratories, from the dwarf galaxies that orbit nearby to the distant galaxies seen at the edge of time. In these systems lie more fossils, more survivors, more anomalies waiting to be uncovered. By looking outward, beyond the halo, we can see whether the cracks in our models are local imperfections or universal truths. The search must expand, for only by stepping into the broader cosmos can we hope to resolve the riddle posed by the impossible survivors. The search for the universe's oldest stars cannot remain confined to the Milky Way. Our galaxy, with its rich halo and its impossible survivors, offers only a local view of cosmic history. To test whether the anomalies we find here are universal or peculiar to our own environment, astronomers must look outward. Beyond the Milky Way lie dwarf galaxies, ultra-faint companions, stellar streams, and the earliest galaxies seen at cosmic dawn. Each of these is a time capsule, preserving conditions that can no longer be found in the crowded disk of a mature, spiral galaxy. Dwarf galaxies are particularly revealing. Compared with the Milky Way, which contains hundreds of billions of stars, dwarfs are small and fragile, sometimes holding only a few million stars, or in the faintest cases, just a few thousand. Their modest size makes them vulnerable to disruption by their giant host, but it also makes them valuable as laboratories. Their shallow gravitational wells allowed them to evolve slowly, retaining the imprint of early enrichment that in larger galaxies was quickly overwritten. In systems such as Sculptor and Fornax, astronomers have discovered stars with metallicities as low as those found in the Milky Way halo. These fossils show that ultra-metal-poor stars are not unique to our galaxy. They are a feature of galactic evolution across environments, Even more striking are the ultra-faint dwarf galaxies. Some of these contain so few stars that they resemble clusters more than galaxies, and yet within them are stars whose chemistry is as primitive as any ever found. In certain cases, the entire stellar population can be explained by the enrichment of a single supernova, leaving behind a uniform chemical fingerprint. In others, the scatter in abundances is wide, evidence that enrichment was patchy and stochastic. One galaxy might contain stars enriched in carbon but lacking iron, while another hosts stars showing the rare fingerprints of neutron star mergers, which forged heavy elements like strontium and barium. This diversity underscores a central truth. Chemical evolution in the early universe was messy, not smooth. Small systems preserved the randomness of their few enrichment events, creating a living archive of variety. The universality of the impossible survivors is tested most clearly in these dwarfs. Stars with iron abundances less than 1/10,000th that of the Sun have been found in several systems, proving that the same extreme conditions that produced the Milky Way's most primitive stars also existed elsewhere. Their presence across multiple galaxies confirms that the processes capable of creating such survivors were widespread. This is crucial, for it shows that the cracks in our models are not artifacts of a single galaxy's history, but reflections of physics that shaped the entire cosmos. Beyond the local group, astronomy pushes further back in time. The James Webb Space Telescope has opened a window onto galaxies, seen as they were less than 500 million years after the Big Bang. These systems are faint, redshifted into the infrared by cosmic expansion, but their light carries powerful clues. Some appear far brighter than expected for their age and size, as if powered by stars of unusual mass and heat. Their spectra show strong hydrogen and helium features but little evidence of metals, consistent with what would be expected from population 3 stars. While the evidence is not yet conclusive, it is tantalizing. For the first time, we may be glimpsing the light of the very first stars, not as fossils, preserved in our own galaxy, but directly in their original habitats. Future instruments will sharpen this view. The extremely large telescope, with its 40-meter mirror, will probe stars in nearby dwarfs with unprecedented resolution, measuring abundances with exquisite precision. The Vera Rubin Observatory will scan the sky repeatedly, revealing faint galaxies and stellar streams too dim to have been noticed before. Together, these observatories will expand the fossil record far beyond the Milky Way, showing us whether the lessons of our halo apply across the universe or whether our galaxy is exceptional. This outward gaze is not a detour from the mystery of the impossible survivors, but an expansion of it. If stars like Hey 010752440 and SDSS J102915+172927 are found in dwarfs and in distant galaxies, then they are not peculiarities of the Milky Way. They are universal markers of the early cosmos. If, on the other hand, our galaxy alone harbors them, then something unusual must have occurred in our history, making us a rare case in a universe that otherwise followed different rules. Either way, the pursuit deepens our understanding. The philosophical resonance of this search is profound. When we study stars in distant galaxies, we are extending memory itself. We are looking back to a time when the universe was still assembling its first structures, when hydrogen and helium dominated, when the first heavy elements were only beginning to appear. Each fossil star in a dwarf galaxy is a witness to this era, a living remnant of processes that occurred more than 13 billion years ago. Each spectrum is a record written in light, carrying across cosmic time the story of creation. And yet, even as these discoveries accumulate, the mystery is not resolved. We still do not know whether any star we see today is a true population 3 survivor. We do not know whether faint supernovae or dust cooling were the decisive mechanisms, whether turbulence or dark matter altered the pathways of star formation, or whether processes we have not yet imagined were at work. The fossils we find in other galaxies are essential clues, but they are not final answers. They expand the puzzle rather than complete it. To look beyond the Milky Way is to accept that the universe is far larger than our theories. The impossible survivors, whether found here or in other galaxies, remind us that the cosmos is inventive, producing outcomes that challenge our neat categories. Their presence across multiple systems confirms that what we face is not an anomaly, but a universal mystery. They are not curiosities of one galaxy, but voices of the cosmos, speaking the same language of defiance from Sculptor, Fornax, Segway 1, and from galaxies seen at the edge of time. The journey outward thus returns us to the central paradox. Stars exist that should not, and they do so not only in our galaxy, but across the universe. Their light shines as an invitation, telling us that the first chapter of stellar history remains unwritten, waiting for us to piece it together, from fossils scattered across space and time. Beyond the Milky Way, the impossible survivors continue to remind us that the universe is not finished, surprising us. After all the observations, surveys, and theories, the stars that should not exist continue to stand as enigmas. Their spectra have been measured, their motions mapped, their places in the halo and in dwarf galaxies charted, and yet the central questions remain unanswered. The impossible survivors sit at the boundary between prediction and reality, insisting that our models are incomplete. They remind us that the first 100 million years after the Big Bang are still shrouded in uncertainty, and that our understanding of cosmic history is more fragile than we often admit. The foremost question is whether any of the ultra-metal-poor stars we see today are true population. 3 survivors. Theory has long maintained that the first stars were massive giants, burning hot and dying young, leaving behind no survivors for us to see. Yet the chemical poverty of stars like HE01075240 or SDSS J102915+172927 challenges that certainty. If even one such star formed directly from pristine hydrogen and helium and managed to endure, then it is a living fossil of the universe's dawn. But how can we know? Accretion of trace metals over billions of years may blur the line, leaving us uncertain whether we are looking at the first stars or their immediate descendants. The second question concerns faint supernovae. The abundance patterns in many ultra-metal-poor stars suggest enrichment from explosions that ejected carbon and magnesium but held onto iron. Were such supernovae common? Did they play a decisive role in seeding the cosmos with the ingredients needed for cooling and star formation? Or are we misinterpreting the evidence, imposing models where the true processes were different and perhaps stranger? Without a clearer understanding of how the first supernovae unfolded, the fossils remain ambiguous. Dust is another unresolved mystery. Some models suggest that the first explosions created dust grains, tiny solids that provided powerful cooling pathways. Dust would have allowed gas clouds to fragment into smaller clumps, birthing low-mass stars able to endure for billions of years. But how much dust did the first stars produce, and how much survived the shock of their deaths? The balance between fragile survival and destructive violence determines whether dust was the key to longevity or a marginal factor. The diversity of chemical fingerprints among the impossible survivors also demands explanation. Some stars show high carbon and low iron, others are enriched in heavy elements from rare processes, like neutron capture, while still others seem almost entirely barren of metals. Why is the fossil record so varied if the early universe was seeded by only a handful of massive stars? Does this diversity reflect a patchwork of enrichment, where isolated pockets of gas evolved independently, or does it point to processes we have not yet included in our models of stellar birth and death? Dark matter adds another layer of uncertainty. The first stars formed in dark matter halos, and the nature of that invisible substance shaped their environments. If dark matter interacts only through gravity, star formation proceeds one way. If it has more complex properties, the pathways could be very different. Could the existence of impossible survivors be indirect evidence of exotic dark matter physics? It is a radical idea, but one that cannot yet be ruled out. Even the great event of reionization, when the universe became transparent to light, is bound to these questions. Were population 3 stars the primary drivers of reionization, flooding space with ultraviolet radiation, or did early galaxies take the lead? The answer depends on how diverse the first stars were, how long they lived, and how much energy they released. If low-mass survivors existed, then the balance shifts, altering the timeline of cosmic transformation. These questions persist not because of failure, but because of success. Observations have reached a precision where anomalies stand out, forcing theory to adapt. Surveys have become large enough to show that impossible survivors are not isolated curiosities, but part of a broader pattern. Instruments like the James Webb Space Telescope have carried us close enough to the cosmic dawn to glimpse galaxies that may contain the very stars we seek. And yet, in all this progress, the riddles grow sharper. The persistence of these mysteries is not weakness but strength. Science advances by confronting what it cannot yet explain. The impossible survivors are therefore not frustrations but gifts, anomalies that drive the refinement of models and the invention of new ideas. They are the questions that remain, open doors into the unknown. Their endurance across 13 billion years is a reminder that the universe holds its secrets not to deny us, but to invite us deeper. And so the puzzle continues. Are the survivors we see today primordial or second generation? Did faint supernovae or dust cooling shape their birth? Is dark matter implicated in their existence? How rare are they, and what do they mean for the timeline of cosmic history? None of these questions has a final answer. What we have instead are clues, fossils, and paradoxes, all pointing to a universe richer than our imagination. The questions that remain define the frontier of astrophysics. They are the horizon we chase, the horizon that retreats even as we approach. The stars that should not exist stand at that horizon, their faint light challenging us to follow. They are puzzles, but they are also promises, telling us that the universe has more to reveal, that discovery is not over, that wonder is not exhausted. At the end of this journey, after the discoveries and the doubts, after the fossils and the theories, what lingers most is not frustration, but wonder. The stars that should not exist do not diminish our understanding of the universe, they expand it. They remind us that science is not a finished edifice but a living process, a dialogue between what we expect and what reality delivers. At the edge of knowledge, anomalies are not flaws, but sparks, illuminating paths we did not know were there. To look at an ultra-metal poor star is to look across nearly the whole age of the universe. These stars have endured for more than 13 billion years, shining through the collisions that built the Milky Way, through the birth and death of countless suns, through the formation of Earth and the rise of life. Their light left them long before there were eyes to see it, and yet it arrives now, carrying with it the story of the cosmos's earliest days. That endurance is itself a miracle of physics, a testament to the capacity of small stars to outlast the giants around them. The wonder lies also in what these survivors represent for humanity. From the first people who traced constellations across the night sky to the astronomers who now map spectra with precision, we have always sought meaning in the stars. Ancient cultures saw gods and heroes, while we see nucleosynthesis and metallicity, but the feeling is the same: awe before lights that burn across eternity. The impossible survivors are part of this continuity, carrying both the weight of science and the poetry of mystery. There is humility in realizing that the universe is more creative than our equations. For decades, theory insisted that population 3 stars could not leave behind low-mass survivors. Yet, here they are, faint but stubborn, defying expectations. They remind us that the cosmos is not bound by our categories. It writes its own script, and our task is to read it, to revise our models until they reflect the richness of reality. In this way, the impossible survivors are teachers, not obstacles, guiding us toward deeper truth. The edge of knowledge is not an ending, but a horizon. Beyond it lies more to discover, more to question, more to imagine. The cracks in our models are openings, not failures. The unanswered questions are invitations, not dead ends. The survivors of the early universe stand at that horizon, urging us forward, their faint light whispering across time. Seek more, look deeper, do not stop. What makes this wonder profound is that it belongs to all of us. The same light that reaches the spectrographs of great observatories also reaches the eyes of anyone who looks up at the night sky. The connection between humanity and the stars is unbroken, whether through myth or through science. The impossible survivors strengthen that connection, for they remind us that even the smallest points of light can carry the weight of cosmic history. And so we end not with certainty but with awe. The stars that should not exist are anomalies, puzzles, defiant survivors, but above all, they are gifts. They show us that the universe is still speaking, still holding secrets, still inviting us into wonder. To stand beneath their light is to stand at the edge of knowledge, where science and imagination meet, where questions become promises, and where the cosmos reveals itself not as a solved riddle but as an endless source of discovery.